Seeing.
Ziyin, okay.
just let people filter in another minute or so, and then we'll get started. Okay, thank you all for coming. And congratulations on correctly identifying the awesome session. Yes, okay. So we have some really super cool papers today. The first one is by Ziyin. So I did a lot of work a long time ago on topic models back when people thought those were cool, and everyone kept asking, how many topics should I use? And so it was really confusing to me when embeddings sort of took over the world, which are almost exactly the same model, that nobody seemed to care about the dimensionality. Nobody. So I'm really excited to see this paper. So Ziyin, take it away.
Thank you. Hi, everyone. Hope you all enjoyed your time at the conference so far. My name is Z, and today I'm going to introduce our work on word embeddings. This is a joint work with Yuan Shen from Stanford. Embedding methods has become a universal tool in NLP, especially in this current deep learning age. It turns discrete tokens, like words, into vectors in the Euclidean space. The vectors can then be used to discover various relations between words, like word relatedness or word analogy. Moreover, these vectors can be used as inputs to neural networks, which is a pretty standard training technique for deep learning models in NLP. But although embedding methods are playing such an important role, there's not much understanding about them. People have empirically discovered that embeddings tend to have an optimal dimensionality in terms of performance. This means if you choose a dimensionality that's either too small or too large, the performance of your model will get hurt. Now, this is a classical hyperparameter tuning problem where you see pretty much everywhere in deep learning. And people sometimes don't like this because they feel more like magic than science. Finding the optimal dimensionality for word embedding is very difficult in practice. So what people usually end up doing is just to do some simple grid search or just pick their favorite numbers, like 300 or 200 or 400. And this can be problematic because when these numbers are chosen, there is essentially no guarantee that your model has the best performance. So we need a more principled approach for this specific hyperparameter tuning problem. Now, in this work, we study word embedding from a theoretical point of view. Specifically, we prove mathematically that there exists an optimal dimensionality, and we provide a way to find it. And we also use our framework to quantify other aspects of word embedding, like their robustness to overfitting, which is also very important practically. The main object we study here is the embedding matrix. Now suppose we have a vocabulary of n words. The embedding of the ith word wi is a vector vi. Now if we stack every vector from v1 to vn on top of each other, we get the embedding matrix, which we call E. And remember, this is the same embedding matrix when you train your neural network in TensorFlow by calling this embedding lookup operator. And our goal here is to understand the relation between the embedding matrix and its dimensionality. So how do we approach this problem? Well, we got our intuition from classical statistic estimation problem, where there is an unknown parameter theta star we want to estimate. And the solution usually has 3 steps. First, we define a class of estimators, and then we define a loss function, and then we choose the estimator that minimizes the loss function. So can we do something similar for word embeddings? Now suppose there is an unobserved ground truth embedding E star. And during the learning phase, we obtain the trained embedding E hat using an algorithm like word2vec on a corpus like Wikipedia. Our goal here is to choose the dimensionality of E hat in order to make E hat as close to E star as possible. In order to do so, we need to fill in the missing steps of the statistical procedure. Specifically, we need a loss function in order to measure the closeness between embeddings. And we also need a way to estimate the loss function in order to choose the dimensionality. So now let's look at the first problem. Finding a loss function for embedding may seem pretty straightforward at a first glance. Since embeddings are essentially matrices, can we just directly compare them and take a matrix norm? Well, the answer is no, because embeddings are inherently unitary invariant. For example, if you train your word embedding, and then you rotate it by 180 degrees, they are essentially the same embedding, but the difference between them can be pretty large, and this is undesirable. So to address this problem, we propose the pairwise inner product, or the PIP loss, which has this expression. Now, it may not become immediately clear why this is the right thing to do, so let's take a step back and see what was wrong with the original formulation. Now, when we have two embeddings, E1 and E2, they are implicitly placed into separate and possibly different coordinate systems. And this actually prevented us from directly comparing them, because a simple change of coordinate will make the results completely different. An analogy of this phenomena is Newtonian mechanics. And we all know that taking measurements between objects in different frames are very difficult because the result of the measurement depends on which frame it is being taken. And the solution in physics was to use relativity. So now let's go back to word embeddings. What we can do here is to first put every vector in a relative coordinate system before we compare them. And this is exactly what the PIP loss does. So in order to see this, let's look at the ith row of the difference matrix in the PIP loss. The ith row of E1 transpose is essentially the relative coordinate of the ith vector Vi, measured against every other vector, and it is the same for the ith row of E2 transpose. Now, when we take the difference, we are essentially measuring by how much the ith vector Vi has shifted between the two embeddings, using every other vector as anchors. And by doing so, we remove the dependency on a specific coordinate system. And this is the theoretical intuition and geometric interpretation behind the PIP loss. So at this point, some people may argue that they are practitioners, and theory is not really important. As practitioners, what they care about is what you can do with word embeddings. For example, solving natural language tasks like word relatedness or word analogy. We found that these natural language tasks are highly related to vector inner products, which the PIP loss tightly controls. So if you want your training embedding to perform similarly to the ground truth embedding, you also want to make sure that the PIP loss between them are small. So from both theoretical and practical point of views, the PIP loss is the right loss function. Now we have a satisfactory answer to the first question. How about the second one? How do we estimate the PIP loss? Well, our observation is that if the embedding algorithm uses matrix factorization, then we can use matrix perturbation theory to estimate the PIP loss. Now, recent research has discovered that many embedding algorithms, including word2vec and glove, are essentially doing matrix factorization, either explicitly or implicitly. For these algorithms, a matrix M called the signal matrix is estimated from the corpus, and a low-rank approximation is performed on M, which decomposes M into two components, E and F. If we take the first component, E, that is essentially our embedding matrix. And our main result showed that for embedding algorithms of this category, is PIP loss can be nicely decomposed into bias and variance terms. And moreover, this bias variance decomposition has a nice interpretation in terms of signal and noise. As we increase the dimensionality of the trained embedding, we're including more signal, so the bias term, the term in red, will decrease. But at the same time, we are also including more noise, so the blue terms, the variance terms, will increase. The right dimensionality will strike a balance between the amount of signal and noise included in the training embedding. So what we are looking at is a pictorial example of the PIP loss and its bias variance decomposition. The x-axis is the dimensionality of the training embedding, and the y-axis is the PIP loss. We can see that the loss indeed has two phases. For the part on the left, it has a high bias. For the part on the right, it has a high variance. And notice around dimensionality 700, the PIP loss is minimized, and that is the dimensionality we're looking for. The bias variance decomposition of the PIP loss naturally allows us to answer questions of the following kind. If we have an embedding algorithm and a corpus, how do we choose the dimensionality? Our solution has two steps. First, we estimate the signal and noise which are needed in order to calculate the pip loss. And then we just choose a dimensionality that minimizes it. And this is simply our procedure. In the following experiment, we use our procedure to choose dimensionality for a few embedding algorithms, and we cross-validate our results using empirical grid search. In the empirical grid search, what we're doing is we actually train word embeddings of different dimensionality, and we evaluate their performance on a word relatedness test. This word relatedness test will tell us what are the dimensionalities that perform optimally, and then we can cross-validate between our approach and this empirical grid search to see if they agree with each other. And we did our experiment for 3 popular embedding algorithms, GLOVE, Word2Vec, and LSA. From the table, we see that not only the 2 methods, our method and the empirical grid search, agree with each other pretty well, but more importantly, the dimensionalities selected by our method perform almost optimally on the word relatedness test, and it is 50 times faster. Now, in the paper, we also have other findings about word embeddings. For example, we proved that Word2Vec and GLOVE are robust to overfitting. We also use our pip loss technique to find various linguistic shifts and domain adaptation phenomena in language, but we will skip the results for now. And finally, we have good news for everyone. We have open sourced our tool for dimensionality selection, which you can find through the link on the through this GitHub link, and I will stay on this the slide for a while so that you can take a picture of it. So now, next time when you train your word embedding, you no longer need to select 300 as your default dimensionality. There is a way to make your model perform the best in practice. And thank you very much. And that's all. That's my talk.
Great, we have some time for questions. I should also mention I've opened my DMs on Twitter if anyone doesn't feel like asking a question in front of a giant audience. So at @dmimno, M-I-M-N-O. Good.
Hi, thanks, this is really interesting. So one of the things that seems crucial is estimating those signal and noise parameters from the corpus. Can you say something more about what those maybe intuitively represent and how you estimate them?
Sorry, can you repeat the second half of the question?
So those signal and noise parameters that you estimate, how do you estimate those from a corpus?
Sure. So our method will apply for embedding algorithms using matrix factorization. So the signal is essentially the spectrum of the matrix. And for our specific method, we use a paper published by Professor Chatterjee in Annals of Statistics. There is a shrinkage estimator for the spectrum, which is like minimax optimal. And for estimating noise, we also have a pretty standard statistical procedure of doing so. It's like bootstrapping the data. So yeah, we have more details in the paper of how we estimate these parameters.
Hi, thank you for the nice presentation. So my question is, the reason why we pick usually a small dimensionality is for memory consideration. So if your algorithm would recommend using 1,000 lengths of word embedding, then how much gain am I getting compared to the memory usage that my model will start requiring for that? Thank you.
I think for practical purposes, if you only consider word embedding itself, the memory consumption will grow linearly with respect to dimensionality. And if you're training like a neural network on top of the embedding, then it will grow quadratically. So that's also one of the reasons you don't want to pick a dimensionality that is too big, because that's going to blow up your memory and also slows down your inference and training. And from our research, we found that the embeddings are actually pretty insensitive to overfitting, which means if you pick a dimensionality that is too large, the actual performance will not drop by a lot, but it will hurt your like inference time and memory. So still, you want to pick a smaller dimensionality if you can, without sacrificing too much on your performance.
Two more?
Okay.
In the chart you briefly flashed up, the optimal dimension for glove was about 6 times bigger than Word2Vec, and it seemed surprising to me that there was such a huge difference. Do you have an explanation for that?
I think when I look at the parameters of the embedding, like we have like the signal, which is the spectrum of the matrix, and the noise. What's surprising to me is that glove seems to have a significantly lower noise compared to Word2Vec, and that allows you to choose a much bigger dimensionality. And also, this phenomena is not very consistent. So we did our experiment on the like text-aid corpus, where the glove has a significantly lower noise. But on other corpus, like the entire Wikipedia, they actually have similar noise. So on that corpus, Word2Vec and glove actually have pretty similar optimal dimensionality.
Okay, sir, one more question?
Thank you. So there is one other important parameter that has a great impact on the quality of embedding, and that is the size of the vocabulary. And have you done any study on the vocabulary size? And especially the way you calculate the loss seems to be computationally expensive with respect to the vocabulary size. And have you done some analysis on together the vocabulary size and the dimensionality?
Yes, so in all of the experiments, we use 10,000 as our vocabulary size. And we also use larger vocabulary, like 50,000, and we found there's not significant difference. And the reason we use 10,000 is like, it is much faster to do that because there is a matrix factorization in the procedure. But we found that the optimal dimensionality is rather insensitive to the size of dimensionality you pick, as long as you don't increase the noise by a lot, meaning you don't increase too much low frequency words in your corpus.
Okay. Sorry to cut off, but we have 2 amazing spotlights. First will be Yuan Chung. This is one of those papers where I looked at what they were doing and said, no way. But you did it, so take it away.
Hi everyone, I'm Yuan Chong from MIT. Today I'm very honored to have this opportunity to present our paper on supervised cross-model alignment of speech and text embedding spaces. This is a joint work with Wei Hong Won, Stracy Tong, and James Glass. So recent machine learning models have shown great success in tasks such as machine translation, speech recognition, and speech synthesis. However, most of these models still largely rely on sizable sets of parallel corpora for training to actually make them work. For example, in machine translation, this means that an English text needs to be paired with a French translation. And for speech recognition, this means the data has to be in the form of an English audio paired with its transcription. So as you can imagine, this kind of data is very expensive to collect and label, making these state-of-the-art machine learning models hard to be applied to low-resource languages. So in this framework, we proposed a framework that learns to align speech and text embedding spaces. Our framework takes only 2 corpora of speech and text as input, and these 2 corpora, they can be of different languages, and most importantly, they do not need to be parallel. So the first step is to train 2 embedding spaces from their respective modalities. For text embedding spaces, we simply train Word2Vec on the text corpus. So now each word in the corpus is represented as a fixed dimensional vector in the text embedding space that captures the semantics of the word. Here we use a matrix Y to denote the set of text embeddings. For the speech embeddings, we train speech2vec on the speech corpus. Here, speech2vec is combined with an unsupervised speech segmentation algorithm that pre-segments the utterances in the speech segment into audio segments corresponding to words. And then speech2vec is in charge of transforming each of them into word vectors in the speech embedding space. Here we use a matrix X to note the set of speech embeddings. Now that we have 2 independently trained speech and text embedding spaces, we then apply a recently proposed unsupervised bilingual lexicon induction algorithm called Muse to align them. Mathematically, the goal of Muse is to learn a linear mapping W from X to Y such that the F norm of W times X subtract Y is minimized. So Here are the key components of our framework. First, we use Word2Vec to learn distributed representations of words from a text corpus that model word semantics in an unsupervised manner based on a distributional hypothesis such as skip-grams. And for speech-to-vec, it is a recently proposed neural architecture. It can be viewed as a speech version of Word2Vec, but learns semantic word representations from speech corpus. It is also unsupervised and based on the distributional hypothesis used to train Word2Vec. Finally, Muse is an unsupervised way to learn the alignment W with the assumption that the two embedding spaces are approximately isomorphic, which means that the two embedding spaces have similar shapes. So here are the advantages of our framework. First, it relies only on monolingual corpora of speech and text. The two corpora do not need to be parallel, which means that they can be collected independently and thus greatly reduce human labeling efforts. Secondly, the framework is unsupervised since each of its components uses unsupervised learning, making the framework very applicable to low-resource language pairs that lack bilingual resources. In this paper, we show such alignment can be used in two different tasks, depending on the source of the corpora used for training it. When the language of the two corpora are from the same language, say English, and given an audio segment corresponding to an English spoken word like dog, it is first transformed into a speech embedding into the speech embedding space by speech-to-vec. And since now the speech and text embedding spaces are already aligned by W, we can perform nearest neighbor search and retrieve its nearest neighbor in the text embedding space. We hope the system can return words that are semantically similar to the original audio segments, such as dog, dogs, puppy, with the hope of the word dog as the top rank. And when the languages of the two corpora are different, say English speech and French text, given an audio segment corresponding to an English spoken word dog, following the same principle as mentioned for the previous task, we hope the system can return its French translation. And we believe our work provides an alternative way to achieving unsupervised or weakly supervised speech recognition and unsupervised speech translation. So we hope to see you at our poster for more details. Right, thank you.
Next up, we have another really interesting application of aligning different things into the same vector space. We have Xinyuan Zhang.
Hello everyone, I'm Xinyuan Zhang from Duke University. Today I'm presenting our paper, Diffusion Maps for Textual Network Embedding. This work is collaborated with Yitong Li, Ding Hanshen, and Dr. Lawrence Karen. Networks are everywhere in our world, such as social networks like Twitter or citation networks like Archive. A textual information network can be represented with V, a set of vertices, E, a set of edges, and T, a set of tags associated with vertices. Network embedding aims to learn a low-dimensional representation for each vertex. Existing textual network embedding methods either embed text independently using traditional NLP approaches or only consider the relationship between two linked vertices. So the problem is, how can we measure the complete level of connectivity between any two texts in the graph? To address this problem, we propose DMTE, which captures the semantic relatedness between texts by applying a diffusion convolutional operation on the text inputs. Also, we design a new objective that preserves high-order proximity by including a diffusion map in the conditional probability. An important notion of our method is transition matrix, which is obtained directly from the graph with Pij representing the transition probability from vertex Vi to vertex Vg within one step. The diffusion process is achieved using the power series of P. In this example, initially the vertex 2 is inactive since it only connects with vertex 1. Through the diffusion process, information is delivered from active vertices to inactive ones, so we can see the smoothing effect in the fourth-order diffusion graph. In our paper, the diffusion map of vertex Vi is Ui, which maps from vertices and embeddings to the results of a diffusion process that begins at vertex Vi. Our model DMTE is shown in this figure. To incorporate both structure and text information of the network, we adopt two types of embeddings, Vs and Vt, for each vertex. The structure embedding table is learned during training. For text embedding, we first get initial text representations X from the learned word embedding table using some NLP approach such as word embedding average or LSTM. Then we apply a diffusion convolutional operation on the text representations to build long-distance semantic relatedness. The final embedding of the vertex is the concatenation of Vs and Vt, which can be used directly as a feature vector for various tasks. Given a set of edges, the goal of DMTE is to maximize this overall objective function. It consists of 4 parts for both structure embeddings and text embeddings. Each part is to measure the log likelihood of generating Vi condition on Vj. Please note that here, the LSS and LTS, we use US instead of VS, which computes the probability condition on the diffusion map of vertex Vj. We conduct experiments on 3 real-world networks for 2 tasks. Link prediction, where we predict the existence of an edge given a pair of vertices, and multi-label classification, where we predict the label of each vertex. Our DMTE model outperforms all baseline methods on these tasks. This table shows the most similar vertices for a given query vertex based on the learned embeddings. Some of them are neighbors of the query vertex in the graph, some of them are not, but they are semantically close to the query text. So the embeddings learned by DMTE successfully incorporate both structure and text information. If you're interested to know more details and have any questions, please come to our poster later. Thank you.
Big thanks to Yuan and Xinjuan. Our last paper of the session is a super exciting one again. Yeah. So how many people love autocorrect? Predictive texting, so much fun. Wouldn't it be cool to do that for code? Yeah, okay. It's coming, you know it's coming, but we want it done right. And Tatsunori Hachimoto is going to tell us some work on going towards predictive coding.
Okay, thank you very much. Thank you everyone for coming. I'm Tatsu, and I'm really excited to present to you our work on a retrieve and edit framework for predicting structured outputs. This is joint work with my wonderful co-authors, Kelvin, Jonathan, and Percy. So sequence-to-sequence models have achieved remarkable accuracy gains over the last several years in tasks ranging from machine translation, summarization, to dialogue. And because of these gains in performance, there's been a growing interest in predicting longer and more structured sequences. An example of such a task is shown here from the Hearthstone card prediction dataset, where the input is a structured metadata representing a card from a computer card game, and the output is a Python class which encapsulates the various attributes and executable functions of this card. As you can see, this card is generally long and has some long-range dependencies, like having to copy over the name several times and having consistent attributes. In addition to this, the dataset sizes of these types of structured prediction tasks are on the order of thousands rather than millions, which makes tasks of this kind very hard. When we attempt to directly generate code of this kind using sequence-to-sequence models, we can observe several types of failures. So let's say we're trying to generate this particular card called the Spellbreaker here, and we don't really know very much about this task. All we know is that it's Python code. We don't know what the underlying API is or what style to be using. In this case, what we might have is that we might only know about certain generic things that we can do. And if we apply a sequence-to-sequence model, these types of failures often happen, where we get a generic output that might correspond to something like an almost empty function with a generic constructor and a function. This has really been observed in a variety of different areas in natural language processing. For example, in dialogue systems, there's a very well-known problem known as generic utterances, where if you drive a dialogue system to a state that it hasn't seen before, it will immediately respond with something like, I don't know what you're talking about, which is a generic utterance that's broadly appropriate but incorrect in this setting. And so because of this, we might conclude, well, directly generating the sequences using a sequence-to-sequence model might not be the best idea. So instead, we might fall back to something that's more reliable and classical, like retrieval. So we'll take our inputs and look for something that's generally similar and return this as being the correct output. And so this example is shown here on the bottom, but this has many factual inaccuracies. It doesn't have the right name or the attributes. And therefore, we might say that this also has some drawbacks. So the point of this talk is to think about how can we try to retrieve things, but still have the correctness with respect to the input. So this is a framework that's generally known as retrieve and edit. And I'll go through the framework in detail now. So we're given some input, such as sum the first two elements in the array temp, and we're supposed to generate some code that matches this description. And this is passed to a retriever, and we'll describe what the retriever is later, but it goes through the training set and finds some example that's appropriate. And given this retrieved example, there's an edit model, generally something like a neural sequence-to-sequence model, that combines both the input and the retrieved example and generates an output that's appropriate for the current input. Of course, this is not a new idea at all. Anyone in the NLP community in the audience will say this was done in the exemplar-based machine translation systems of the 90s, and that would be entirely correct. And there's also been recent work applying this to machine translation and dialogue settings. And so these types of works have expanded the applicability of retrieve and edit type models to various tasks and improved the editors. In this talk, we're going to focus on the retriever. What makes a good retriever for a retrieve and edit model, and can we learn a reasonable retrieval mechanism? So there are two main challenges with trying to learn a retrieval mechanism directly from a loss function. So if we look at what kind of losses we have, we'll have something like a log loss that's shown here. This is the expected log loss that we incur when we retrieve and edit. We immediately see that the retrieval is in the bottom of the expectation here, which is a somewhat challenging reinforcement learning style problem. We need to check all the different things we can retrieve in order to know if it's good. So that's difficult to train. But maybe we can apply something like learning to rank to learn that. Even if we could do that, though, the problem is that the retriever and the editor depend on each other. Fundamentally, we need to know what examples are easy to edit in order to train a retriever, and we don't know what examples are easy to edit unless we've trained an editor, which requires a retriever. And so there's this chicken and egg problem between the retriever and the editor that we must first resolve. So how do we do that? Well, we can do that by decoupling the loss. What we're going to do is instead of optimizing the retriever directly, or retriever and editor jointly, what we're going to do is optimize the retriever for an oracle editor. We'll describe this later, but broadly the idea is that we'll just train the retriever against the information theoretically optimal editor that we could possibly have. And then in order to make training a retriever easier, instead of training over all possible retrieval mechanisms, we're only going to consider ones that embed instances in a continuous space and retrieve according to nearest neighbor mechanisms. Now, what is this oracle editor that I just described? Well, we can think in terms of graphical models. So we're given an input x, and the data generating distribution will generate a label y. The retrieval mechanism that we have, whatever it may be, will generate a distribution over retrieved examples x prime, y prime. Performing posterior inference to get the distribution over y is the oracle editor. And this corresponds in some ways to the information theoretically optimal prediction of the output y from our retrieved instances x prime, y prime. The objective corresponding to this is just substituting our oracle editor for the normal editor, and this is equal to the negative of the conditional entropy of y given our retrieved instances. What we're going to do now is we're going to try to optimize for the oracle objective, that is find a retriever that returns informative examples by lower bounding this quantity. Our first result is a decomposition of this oracle loss. What we have is that if you have an encoder and a decoder, you can find a variational lower bound to the oracle loss, or the oracle objective, that consists of two terms. The first term is a reconstruction objective, in which we're measuring the embedding quality. If you look at the first line here, this is just a standard encoder-decoder loss, in which you're taking an input x, encoding it to a vector v, and then decoding it again. And so this measures the quality of the embedding spaces that we're going to be using. The second term corresponds to, in some sense, to the retriever quality. What we're measuring is the distance between x and x prime, sort of being loosely used there, where we're measuring the KL divergence between two embedded distributions. So the closer these are, the higher quality of the retriever. So in order to optimize this lower bound, we're going to take a two-stage approach. First, we're going to maximize L reconstruct, and then we're going to minimize L discrepancy. I'll describe this in two steps. So the first step is trying to learn the encoder. Well, there's an issue with trying to decouple the lower bound. The problem is that the encoder parameters are shared across both of these two terms. And this sort of makes sense because you need the encoder in order to measure the reconstruction loss, and you need the encoder in order to learn to retrieve. So we're going to do something slightly naive and then pick a relatively loose lower bound to start our optimization. What we'll do is we'll pick an encoder with a bounded KL divergence, which will let us set this L discrepancy to a constant for the purpose of getting a lower bound. And then we'll optimize L reconstruct with respect to this objective. So this raises the question, what types of encoder distributions can we choose that will give us exactly this form? What we're going to do is we're going to choose a particular type of distribution, the von Mises-Fisher distribution. This is a directional distribution on the unit sphere in d dimensions, and it is an exponential family distribution. The density function is shown on the top. The picture below shows an example of such a distribution in 2 dimensions, and you can see in some sense that it's a density that decays according to the inner product with respect to the mean vector. What we show in our paper is that the KL divergence between 2 von Mises-Fisher distributions is the squared L2 distance. And this is an important property because it will make it so that the optimal retriever is going to correspond to a nearest neighbor retrieval mechanism. And so the implication here is that once we train our encoder-decoder model by optimizing L reconstruct, then our lower bound looks like the following form, this equation on the bottom here. And what this has is a second term, which depends only on the L2 distance between our query x and our embedded example that we're retrieving, x prime. And the thing that minimizes this loss is just retrieving according to nearest neighbors. And so this leads us to our overall training procedure, which is fairly straightforward. So first, we're going to maximize the loose lower bound by training an encoder-decoder to embed x to a latent space v and then reconstruct y. The key step here is to use a distribution that lets us express the KL divergence as a metric. And then we're going to set the retrieval to be the nearest neighbor index that corresponds to this metric that we defined before. In this case, it's going to be the L2 squared on the unit sphere. And finally, given this retriever, what we can do is we can construct a training set for the editor. We'll go through our input examples, retrieve nearest neighbors, and use these 2 pairs as a way to train the editor. And the training mechanism here is just going to be standard sequence-to-sequence training. So how well does this work compared to sort of reasonable baselines for this generation task that we've been talking about? What we did was we collected a data set of GitHub Python functions from Google BigQuery, filtering for both duplicates and function length. What we got was 75,000 Python functions with restructured text formatted comments. You can see the input on the top left there. We're going to evaluate this as a text generation task rather than a program synthesis task because our initial motivation was to try to synthesize these complex text tasks rather than to do program generation directly. And so what we're measuring here is the number of tokens that were being consecutively completed given partially written code. So you can see in the middle, this is some partially written code, and the bottom, we're trying to complete this as much as possible. And what we find is that sequence-to-sequence is actually surprisingly good. For being sort of raw scraped functions, it can complete 2.5 tokens on average and achieves a BLEU, which is a 4-gram overlap measure of about 20. If we apply just a naive retriever, which retrieves based on a bag of word vectors, we find that the average completion length is 3.4 and BLEU is about 23. Our trained retriever improves this further. And if we combine everything and use retrieve and edit, we get substantial improvements over all the baselines that we tested. And so we find that combining retrieval and editing gives us performance boosts in this somewhat challenging generation task. But you might say, this is a data set that you constructed, so I don't really know what the numbers mean. So we can compare also on a more common benchmark, which is the Hearthstone card generation data set. So this is a data set originally proposed in Link 2016, and the inputs correspond to the structured metadata. So you have this card Spellbreaker, which has some attributes, as well as a description. And the description generally corresponds to an executable piece of code. And what we're supposed to generate is a small Python class that encapsulates all of these facts. We find, once again, a very similar trend, which is that the sequence-to-sequence model does achieve reasonable accuracies. It achieves a BLEU of 60, which is pretty high for this task, but the retriever actually does better because of the high overlap between cars in this data set. If you improve the sequence-to-sequence model doing things like entity tracking, you can get performance that's above retriever, but we find that retrieving and editing using the 3-stage process we described actually improves performance beyond that of all of the sequence-based baselines that we tested. But that's not really the complete story, because there's been a substantial amount of work in the last several years on this Hearthstone cards data set using abstract syntax trees, which is the graph-based underlying representation of Python code. So if you use this problem-specific information, you can get substantial performance improvements over all of the sequence-based methods, including ours. And so retrieval and edit is not really a replacement for a problem structure, but what we find is that we can get substantial boosts to the base model, which is sequence-to-sequence. So if we look at the examples, we find that the retrieved prototypes are pretty reasonable. It's the same type. It's a minion and has a battle cry. And the editor corrects all of the errors that we have. To sum up, what we find is that retrieval baselines are surprisingly strong on these types of challenging structured prediction tasks like code generation, and that retrieval and editing can boost the performance of a base model, such as sequence-to-sequence in these settings. Conceptually, the things that we're proposing here is that you can learn task-specific retrieval by doing encoder-decoder models. And noisy encoder-decoders can map editable examples to nearby so that nearest neighbor retrieval mechanisms can actually retrieve these examples. Thank you.
Okay, we have time for a couple questions. Am I allowed to ask a question? That's what, yeah. Hero here, okay.
Yeah, so this is a great paper. So in automated program generations, there are procedures where you retrieve a code and then you do genetic programming to edit the code. Like you can use other templates-based programs or something else. So did you try those baselines?
No, we weren't comparing to the program synthesis baselines, of which I know there are many, mainly because we're interested in this as a sequence-to-sequence generation task. And so really the question we were interested in was, you have a base model like sequence-to-sequence, can you try to boost the performance of that model? So we weren't comparing to a lot of the program synthesis baselines. In the future, we would probably like to.
Yeah. All right, thanks.
While everyone's heading out, let's just give Tatsu a hand one more time. And if there's more questions, we'll be up here.